Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about rules for aromaticity. So let us start learning of rules of aromaticity. Rules for aromaticity, the four key factors. In the last, we introduced the concept of aromaticity, a properties of some unusually stable organic molecules such as benzene. Although some aromatic molecules are indeed fragrant, the term aromaticity actually has nothing to do with smell. We saw that aromatic molecules have an extremely high resonance energy, 36 kilocalorie per mole for benzene, undergo substitution rather than addition reaction, and have delocalized pi electrons. So we also gave a few example of other molecules beside benzene which are aromatic and some which look similar to benzene, cyclooctatetraene, which are not. So what are the rules? How can we predict whether a molecule is aromatic or not? So summary requirement for aromaticity. In order to in order for a molecule to be aromatic, it must fulfill four conditions. It must be cyclic. You can see this cyclic and acyclic. There must be conjugation all the way around the ring. So every atom in the ring must be able to participate in pi bonding. You can see here has 4 sigma bond. So it is second one is not possible. Now the number of pi electron must be 2, 6, 10, 14, 18 or any higher number in that series, which is often abbreviated for n plus 2 and called Haeckel's rules. So 2 pi electrons, 4 pi electrons not, 6 pi electrons, 8 pi electrons not, and 10 pi electrons. It must also be flat, which is almost always the case if the first three conditions for aromaticity are satisfied. So let us start learning step by step. Four key rules for aromaticity. There turn out to be four conditions a molecule must meet in order for it to be aromatic. It's all or nothing if any of these conditions are violated. No aromaticity is possible. First, it must be cyclic. Second, every atom in the ring must be conjugated. Third, the molecules must have 4n plus 2 pi electrons. And fourth, the molecule must be flat. Some examples of aromatic compounds here: naphthalene, furan, indole, and pyridine, tropylium cyclopentadienyl anion. Counter examples like cyclooctatetraene, not aromatic. So condition 1 for aromaticity, the molecule must be cyclic. Determining if a molecule is cyclic is pretty straightforward. Is there a ring? If yes, move to condition 2. If there is no ring, forget it. Case in point 2, Z135 hexatriene has the same number of pi bonds and pi electrons as benzene but isn't aromatic. No ring, no aromaticity. So look at here 4 rules for aromaticity. Condition 1, the molecule must be cyclic. So first, benzene is aromatic. Second, acyclic, Z form of 135 hexatriene, not aromatic. Now cyclic, you can see pyrrole, aromatic. Acyclic, not aromatic. So now again tropylium ion. You can see the cyclic, this is aromatic. Acyclic, not aromatic. Now you can see cyclohexene, not aromatic. Tetrahydrofuran, not aromatic. Just to be clear, not all cyclic molecules are aromatic. Now condition 2, for aromaticity, every atom in the ring must be conjugated. Obviously, being cyclic isn't sufficient condition for aromaticity. Just look at cyclohexene above rate, not aromatic. In order to aromaticity to exist, there must also be a conditions ring of p orbital around the ring that build up into a larger cyclic pi system. One way of saying this is that every atom around the ring must be capable of conjugations with each other. There are a few alternative ways to say the same thing. So we can also say every atom in the ring must have an available p orbital and every atom in the ring must be able to participate in resonance. So remember that the available pi orbitals condition apply not just to atoms that are part of a pi bond but also atom bearing a lone pair or radicals or a empty p orbitals. So the key things that kill conjugation is an sp3 hybridized atom with 4 bonds to atoms. Such an atom cannot be participating in resonance. So this is why the lone pair on pyrrole isn't as basic as you would expect a nitrogen to be. So protonation of the nitrogen disrupts the conjugations around the ring, destroying the aromaticity in the process. So, four rules for aromaticity. Condition 2. Every atom in the ring must be conjugated. So, alternative, every atom in the ring must have a available p orbital. Alternative, every atom in the ring must be able to participate in resonance. So, aromatic, all ring atoms conjugated. Not aromatic, nitrogen atom is not conjugated. Aromatic, all ring atoms conjugated. Carbon is not conjugated, sp3. Aromatic all ring atom conjugated. Not aromatic carbon is not conjugated. Aromatic all ring atom conjugated. Carbon is not conjugated. So key things to watch out for an atom attached to 4 bonds, sp3 carbon or nitrogen. Advanced note there are actually several molecules which are conjugated around the perimeter of the ring, but interior carbons are sp3 hybridized. Now you can see the condition 3 for aromaticity. The molecules must have 4n plus pi, 4n plus 2 pi electrons. So the third condition is that the cyclic conjugated molecules must have the correct number of pi electrons. Benzene and cyclooctatetraene are both cyclic and conjugated, but benzene is aromatic and cyclooctatetraene is not. The difference is that benzene has 6 pi electrons and the cyclooctatetraene has 8 electrons. We will explain why this makes difference in subsequent post. So this is aromatic, cyclic conjugated 6 pi electrons, cyclic conjugated 8 pi electrons. Our quick shorthand we often use is to say that benzene has 4n plus 2 pi electrons and cyclooctatetraene does not. However, this term causes a lot of confusion in organic chemistry. I have known students who will stare at a molecules and try to figure out what N is. So N is not property of the molecules. Commenter Clares had a great way of putting it. For n plus 2 is not a formula that you apply to see if your molecule is aromatic. It is a formula that tells you what numbers are in the magic series. If your pi electron value matches any number in this series, then you have capacity for aromaticity. Exactly the magic series 2, 6, 10, 14, 18, 22 and counting up from 4 after that. So 4n plus 2 is the mathematical shorthand for writing out the series 2, 6, 10, 14, 18, 22. We can generate this series by plugging in whole numbers 1, 2, 3, 4 to the 4n plus 2 formula. Those values of n have nothing to do with molecules. We are just using them to generate the series. So n is equal to 0, 2, n is equal to 1, 6, n is equal to 2, 10, n is equal to 3, 14. So number in this magic series are sometimes referred to as Haeckel's number after Erich Haeckel, who proposed these rules back in 1931. The condition that aromatic molecule must have 4 n plus 2 pi electrons is sometimes called Haeckel's rule. In the figure below, molecules which fulfill Haeckel's rule are in green. Those which do not fulfill Haeckel's rule are in red. So, rules for aromaticity. Condition third, the molecule must contain 4n plus 2 pi electrons. So where 4n plus 2 is a formula describing the number series 2, 6, 10, 14, 18, 22, 26. And these are magic number for aromaticity. The number of pi electrons in the molecules must be in this series. In order for the molecules to be aromatic, we often call number in this series Haeckel's number. So 6 pi electrons, 6 pi electrons, 4 pi electrons, 2 pi electrons, 10 pi electrons, 6 pi electrons, 10 pi electrons, 4 pi electrons, 10 pi electrons, 4 pi electrons, 6 pi electrons, and 10 pi electrons. So the number of pi electrons is equal to an odd number pairs, 1 pair, 3 pair, 5 pair, 7 pair. This also produces the series 2, 6, 10 like this. Note that we can count electron in pi bonds as well as electron from lone pairs, so long as the carbon isn't already participating is a pi bond. So the cyclopentadiene anion has 6 pi electrons, 4 from the two double bonds and 2 from the lone pair of electrons. So which electron count as a pi electrons and which do not count? So that seems straightforward enough. However, complication can arise when we have atoms in the ring which both participate in pi bonding, also have a lone pair of electrons, for example. How do we count electrons in the benzene anion below left or pyridine? Do we count the lone pair electrons as pi electrons, giving a total 8, or do we ignore them? So what about the furan, which has two lone pair on oxygens? And what about the pyrrole, which it lone pair on nitrogen, or imidazole with two nitrogens? So how many pi electrons are in these molecules? So 8 lone pair on carbon, lone pair on nitrogens, 2 lone pair on oxygens, and lone pair on nitrogen, and lone pair on two nitrogens. So in order to answer this question, it is important to remind ourselves of how p orbital contributes to aromaticity in benzene. So in benzene, each p orbital is arranged at right angles, 90 degrees, to the plane of the ring. Each p orbital contains a single electrons. We can verify the total number of pi electrons in benzene by counting the pi bonds. 3 pi bonds times 2 electrons, 6 pi electrons total. So how p orbitals contribute to aromaticity in benzene? You can see the benzene top view, benzene side view, and benzene showing p orbital. So each p orbital contains 1 electrons, 6 total pi electrons. Note that CH bond are at 90 degree to the pi system. Only one CH shown to for clarity. Note that the CH bond are at the 90 degree to the pi system. If there was a lone pair where the CH bond is, then it would be able to interact with the pi system at all, which bring us to some electron don't count pyridine and benzene anion. The benzene anion has a lone pair on one of the carbon. This lone pair cannot be in a p orbital since p orbital is participating in the pi system. Instead, it's at 90 degree to the pi system in the plane of the ring. In other words, the lone pair on carbon doesn't count as a pair of pi electrons since it cannot overlap with the pi system. The same is also true for the pyridine, where the lone pair is also at a right angle to the pi system. So, while in each case you might be tempted to say that they have 8 pi electrons, the correct answer is 6. This is Haeckel's numbers, and both of these molecules are in fact aromatic. Now, lone pair in the benzene anion and pyridine are not actually pi electrons. In the benzene, anion, the carbon with the lone pair is already contribute a pi orbital and pi electron to the pi system just as in benzene. The lone pair is at 90 degree to the pi system in the plane of the ring. Since it cannot overlap, its two electrons therefore don't count as a pi electrons. So 3 pi bonds, 6 pi electrons. Lone pair on the carbon is at 90 degree to the pi system, no overlap. So don't count as a pi electrons. Now same is true for pyridine. Here can don't count as pi electrons. Now some example of aromatic 5-member ring. Some molecules with 5-member rings can also present ambiguities. The cyclopentadiene anion has a lone pair on one of the carbon. Can this lone pair contribute to the pi system? Since that carbon is not involved in any pi bonding, the answer is yes. The total number of pi electrons to the cyclopentadiene anion equals 2 for the lone pair and plus the 4 electrons in the 2 pi bonds, giving us a total 6, and this is Haeckel's number, and the cyclopentadiene anion is in fact aromatic. So there are lone pair can be part of the pi system since the carbon with the lone pair is not already contributing a pi orbital to a pi system. So lone pair contributes 2 electrons. When added to 4 pi electrons from the 2 pi bonds, we get 6 pi electrons total, Haeckel's number. In similar situation arises for pyrrole. The nitrogen bears a lone pair but is not involved in a pi bonds, unlike pyridine above. Therefore, it contributes to the pi system and this gives us a total 6 pi electrons once we count for the 4 electrons from the 2 pi bonds. So pyrrole 6 pi electrons. Similar to cyclopentadiene anion. 2 electrons from lone pair contribute to pi system when added 2 pi electrons from the 2 pi bonds. So we get 6 pi electrons total. So a curious case in furan where the oxygen bears 2 lone pairs. Does this mean that furan has 8 pi electrons? No. Why not? Because as we noted above, each atom are contribute a maximum of 1 p orbital toward the pi system. In furan, one lone pair is in a p orbital contribute to the pi system. The other is in the plane of the ring, and this gives a total number of 6 pi electrons. Furan is aromatic, so is thiophene, the sulfur analogous of furan. Here is the oxygen has 2 lone pair, but only one can be part of the pi system. When added to the 4 pi electrons from the 2 pi bonds, we get 6 pi electrons total in Haeckel's rule. So lone pair at 90 degree to pi system don't count as a pi. Finally, there is a imidazole which has 2 nitrogen. One nitrogen, the NH, is not involved in the pi bonds and thus can contribute a full lone pairs, and other is involved a pi bonds and the lone pair is in plane of the ring. This also gives a total number of 6 pi electrons once we count for the 2 pi bonds. Look at here, imidazole 6 pi electrons. So only the nitrogen which is not part of a pi bonds can donate a lone pair of electrons. So lone pair at 90 degree to pi system don't count as pi electrons. Condition for aromaticity, the molecule must be flat. The fourth condition for aromaticity is that the molecule must be flat, planar. The aromaticity is such a stabilizing property that generally a molecule that is cyclic conjugated has 4n plus 2 pi electron. We also be flat. Give a molecule a large enough potential energy well and it will fall into a eventually. It's a bit like a punch line to the old crude joke about why dogs adopt a certain energetically favorable conformation, because they can. As this with vertebrates, the only things that preventing a molecule that fulfill the first three conditions from being flat is if the flat conformations incredibly strain. One example in this category is the molecules known as 10 annulenes, an isomers of which is drawn below left. And the cis isomers, the molecule is cyclic, conjugated, and has 10 pi electrons. But two marked hydrogens bump into one another when attempted to adopt a flat conformation.